Hey physics friends, Mr. Collier here. Today we're going to continue our discussion of circular motion by talking about some new angular quantities, and we might go off on a bit of a tangent. The first thing we'll discuss here is angular displacement, which is delta theta, and it's just a change in angular position. Just like displacement is a change in position, position 2 minus position 1, or final minus initial, and this is the same thing except we're looking at where the rotation of the object is in terms of radians, so this will be in radians. So here we have a circle and you displace from position 1 to position 2, and we can then figure out the total displacement by subtracting the two positions. This can also be positive or negative, just like regular displacement can be, except it's going to be a little bit different. Instead of left and right, we're going to relate it to whether it's clockwise or counterclockwise. So we're going to call counterclockwise positive displacement, and clockwise will be negative displacement. Just like forward, backward, up, down, it's arbitrary. We're just making this convention to be consistent. The next thing we're going to talk about is the average angular velocity. Just like velocity is how quickly something is displacing or displacement over time, angular velocity is going to be the change in angular displacement over time. We're going to abbreviate it with what looks like a little lowercase cursive kind of w. It's actually a lowercase omega, and we can write it this way, but we can also write it a little bit simpler as just change in angular displacement over change in time, and that'll tell you how fast something is moving from an angular point of view, and we'll do a sample problem toward the end here. We're going to measure that in radians per second, or you will sometimes convert it to revolutions per second. So this would be another good equation to get down on the equation card. Knowing how fast something is spinning in like revolutions per second can often be helpful, but sometimes what is better to know is how fast something on the object is going, and we call that tangential velocity. So a linear velocity is displacement over time. We're going to look at the linear velocity of an object that's moving in a circle, and we call that tangential velocity, as in the linear velocity at one point on that circle. We can derive this equation by using things we already know. We know that S equals r theta, and that's like sort of a displacement, a distance, and that theta equals angular speed times time. That's just a rearrangement of the angular speed. So then we can rewrite that as the arc traced out by a circle is equal to the radius times basically how fast it's spinning times how long it's been spinning. From there, we can substitute in, since we know that s is a distance, and distance can be written as velocity times time. We can sub in velocity times time. Now we're going to just cancel out some t's here, and we'll be left with this equation. Another good one for your equation card, we can figure out how fast something is going tangent to the circle if we know how fast the circle is spinning and how big the radius is. You'll notice that since radius is part of the equation, how big the circle is going to affect how fast an object on it is moving. And we'll do some examples in class that'll really, I hope, clarify this. One example I think you can picture without even being in class is the idea of a carousel. You've got horses at different distances from the middle. Which one has the greatest angular speed? Well, from angular speed, they're actually all going the same angular speed, because as the carousel spins, every horse goes all the way around one revolution in the same amount of time. So they both have the angular speed. However, they have different tangential speeds because they're different distances from the middle. The greater the radius, the faster it's going tangentially. So the fastest horse on a carousel ride is the one furthest from the middle. That'll give you the greatest tangential velocity. So now let's take this and do some actual math with it. So you've got two children on a merry-go-round, a boy 3 meters from the center and a girl 6 meters from the center. If the ride makes one rotation every 45 seconds, find the angular speed and the tangential speed. So the angular speed is going to be just the displacement over time, and the angular displacement is one revolution or one rotation every 45 seconds. So 2 pi radians is 1 rotation, and it happens in 45 seconds, which gives you a speed of 0.14 radians per second. Now we could convert that to revolutions per second, but we're going to leave it there as radians per second, and now we're going to turn it into something I think a little bit more useful, which is how fast is the boy and the girl going tangential to it, something in meters per second. So we're going to use our tangential velocity equation, and now we're going to be able to plug in the radius from the numbers up top, and we're going to be able to plug in the angular speed, which we just calculated right there. And now we can see that the boy who's only 3 meters from the middle is going slower than the girl who is 6 meters from the middle. So the further you are from the center, the faster your tangential speed is going. Since angular velocity is a vector, it's going to have direction associated with it, but it's a little bit funky here. Instead of looking at the vector quantity as up, down, left, right, we're going to look at it in terms of the axis of rotation. So not necessarily which direction it's moving, but which axis it's rotating around. So if you look at this picture with a record spinning, it's spinning counterclockwise, but the axis is up and down through it. And the way that we can determine that axis is by using something we call a right hand rule. So what you're going to do is take your right hand and curl your fingers in the motion, in the direction of the motion, and then wherever your thumb points, that will be the axis of rotation. Another concept related to circular motion is the idea of period and frequency. Period is simply a measurement of time, and it's how long it takes for one revolution, one cycle to occur. So it's usually going to be measured in seconds, and you could also say it as seconds per revolution. Frequency is the inverse of that. It's how frequently the thing rotates or revolves. So it's the number of revolutions per some amount of time, typically seconds. So 1 cycle per second is also known as hertz. And you might notice this is also then what we're calculating when we calculate angular speed, except we're doing it in radians. So the equations for these are period equals 1 over frequency and frequency equals 1 over period. They're literally reciprocal ways of talking about the same thing. We can also talk about period and frequency in terms of revolutions per minute, which are not a standard metric thing, but it's very common to see RPMs when we're talking about different objects rotating. And here's one last sample problem. Say you have a DVD that rotates at 200 RPMs. What is its frequency and its period? So remember that frequency and period are inversely related, and what we have here is revolutions per minute. That is how frequently it is rotating. So I'm going to take 200 revolutions per minute. I'm going to convert that to seconds, and I find that it's 3 revolutions per second, or 3.3 hertz. So that is its frequency. Its period then is how long it takes to complete one cycle. So if it's completing 3 revolutions in 1 second, it's going to be completing more than one in a second. And so I take the reciprocal, and I get it takes 0.3 seconds to complete one cycle, which is why it completes 3 cycles in 1 second. All right, so that is it for this set of notes. Let me know if you have any questions, and good luck.